Hello everyone and welcome to our webinar, Amplifier Additive Phase Noise Testing at Mini Circuits. I'm sure as most of you know, Mini Circuits offers hundreds of amplifiers. We offer them in bare die, surface mount, and connectorized. And our applications department gets inundated literally with questions about additive phase noise. And after answering a lot of these questions, I thought this webinar would be helpful to address the three topics we have here. What is additive phase noise? How is it measured? Specifically, how do we measure it here at Mini Circuits? And how is it specified? A lot of the questions that come in aren't really clearly defined. So it indicates to me that there's some misunderstanding or confusion on both parts. The customer not providing it and us not asking for it. So hopefully, at the end of this webinar, we can address those three questions. And to do so, we're going to focus on the bullet items you see here. We're going to go into our test set in detail, explain how it works, why we configure it the way we do. We're going to go into some additive phase noise theory, which I think you'll find very interesting and very helpful. And we're going to follow two different types of behaviors, small signal and large signal. And you can see both of these regions are needed to get a thorough understanding of additive phase noise in amplifiers. So we'll touch on each of these, and hopefully at the end of the webinar, we'll have very good answers to what is it, how is it measured, and how do I specify it. So we'll move on to the next slide. This is our test set. It's physically located in our class 100,000 clean room. So the temperature and humidity are very well controlled. We don't have to worry about that. What's not obvious, this entire test set is mounted on a vibration isolated table, because any type of vibration that comes into either the test equipment or the DUT will corrupt the phase noise measurement. So be very careful about that. Not only that, but you'll notice even the test equipment itself and this EMI enclosure are mounted on vibration absorbing material. So this is our EMI box that the DUT resides within. It's very important that we keep any spurious, any type of electromagnetic interference out of the DUT while we're making these measurements. If you look at the phase noise analyzer itself, you'll notice there are three coaxial cables that are coming out of the analyzer. Those are DC voltages. Very clean, provided by the test set, and we route them into our EMI enclosure and therefore to the DUT through coaxial, well-shielded cable. Very important. Anything on that DC, spurious, will perturb the measurement, and we don't want that. The other thing you'll notice, so we'll go into this front end a little bit more, but you'll notice there are very short coaxial cables, well matched, phase stable, and very short cables that run into the EMI enclosure and back out again. It's very important that we minimize the total phase length from output of the analyzer back into input. And you'll see why as we go through this. What's not shown here is the AC power that powers all this is coming from a conditioner and filter, because we don't want AC noise, again, corrupting the measurement. So if we go to the next slide, we'll kind of summarize what I just spoke about. Short, well-matched, low-loss, shielded, phase-stable cables, very important. Torquing the connectors, I didn't mention this, but it's extremely important. If you're connecting a coaxial connector, male to female, and that connection is loose, you will get nonsense. You will get nonsense below 1 kilohertz and not understand why. They vibrate a little bit, they introduce phase perturbations. Extremely important that we properly torque the SMA shell, male shell to the female. The other thing while you're doing that is you want to avoid putting a torsional stress on the cable, a rotating force on that cable. That is mechanical energy that will be stored in that cable. And at some point, it's going to want to be released either as a phase perturbation or a phase pop. So when you're tightening those connectors, try not to twist the cable when you're doing that. That'll ensure that you don't experience one of these phase pops during the measurement, which means you have to start over again. Suitable EMI enclosure, we talked about that. Well isolated from external mechanical vibration, we talked about that, very important. Temperatures and humidity, very well controlled. And don't touch anything, for the same reason. Don't touch anything or forget it. You're all over, it's all over, start all over again. Some of the specifics of how we configure the phase noise analyzer, really what I want to focus on are the two circled items there. What is my signal source power out of the analyzer? In other words, into the DUT eventually. What do I want to set that to? And what do I want to put back into the analyzer from my DUT? Two very important levels that we'll discuss as we go on. So I said we're going to come back and take a look at the front panel of this. If you notice, we have signal source output. This is the carrier frequency that you've selected and the internal power that you've selected to come out of the analyzer. We have an 11 dB mechanical step attenuator that we have here, along with a fixed attenuator. And between the fixed pad and the mechanical step attenuator, we want to adjust the padding such that the input dynamic range to the amplifier takes us from compression, maybe 3 dB compressed at least, into small signal. If 11 dB is not sufficient, we change the fixed pad and do it over again. You get easily a 20 dB dynamic range by using the 11 position attenuator with the fixed pad. This is 1 dB step. That's going to control the input power into the DUT. What's very important is when you're doing this and selecting a power to be outputted from the analyzer, you do a through path calibration. You replace the DUT with a through. You set this, for example, the maximum is what we start with. And in this case, it's plus 13 dBm. And we look at what comes back out. We configure the attenuators so that what comes back into the analyzer is approximately what we'd expect out of the DUT. We'd like about plus 10 dBm or so. And then we examine the additive phase noise from our instrument noise floor. If we like it, good, we move on to the next carrier frequency. If not, there's a dependency between additive phase noise that we measure in the through path and the signal power coming out of the analyzer. So if we don't like what we see, we lower that power a little bit. Not here, here. Lower the power, run it again. Lower the power, run it again. Ah, that's good. Eventually you will get a trace that you're happy with. You record that. That's the highest I can set this to and achieve acceptable results. If we can do it at plus 13, fine. If not, we lower it. It may impact your input dynamic range, but we're doing that to favor the additive phase noise performance or the noise floor of the system. So again, continuing pretty much what I said, input attenuator and fixed pads, that's the dynamic range into the DUT. The fixed pad and step attenuator on the output sets the signal level back into the analyzer. This ensures that we're always kind of measuring in the same state. The analyzer power that we're inputting is always about the same level. That just makes the measurements more consistent and more repeatable. Uh-oh, we said we're going to go into a little phase noise theory. So here we go. These four graphs are extremely enlightening, and I have to thank Professor Rubiola for these. And we're going to go into each one of these in a little bit of detail, just so you understand what they all represent. So if you look at this first one, this is your spectrum analyzer. Everybody's used the spectrum analyzer, right? No big deal. Set the amplitude, set the span, set the resolution bandwidth, maybe the video bandwidth. We all know about that. So let's assume we're going to do that. But then we're going to take our DUT, we're going to take our amplifier, and we're going to connect the output of the amplifier into the spectrum analyzer. We're going to terminate the input of the amplifier. And we're going to look at the trace. What do we see? White noise, right? We see nice flat white noise, not too interesting. Then we're going to apply power to the amplifier. And what happens? Well, white moves up. We turn power off, it goes down. We turn power on, it moves up. Okay, so what we're seeing is now the noise power output of the amplifier with the application of a DC voltage. Still not terribly interesting from an additive phase noise standpoint, but we'll get to that. Now let's take a regular SIG-gen that we have laying around the lab and just put a signal into the input of the amplifier. what do we see? We see something like this, right? We see energy centered at the carrier frequency, and it has sidebands. Those sidebands are associated with the absolute phase noise of the synthesizer. The additive phase noise would be, what are we doing to that? What are we adding on top of that absolute? So let's pretend for a minute we had an ideal synthesizer that has no absolute phase noise of its own. It's a perfect impulse. We put that into our amplifier. What do we expect to see? A perfect impulse? We'd like that, but we don't. We don't. What do we see? We see sidebands again. Why am I seeing sidebands? I just put a perfect impulse in, yet I see sidebands. That's because, unfortunately, pretty much every electronic component, pretty much everything, exhibits what's known as flicker noise, or 1/F noise. It's there in passive components, and it's certainly there in active components, and it definitely gets worse when there's a DC current applied. Well, amplifiers unfortunately need DC current, right? So the fact that you're biasing an amplifier and you're using active and passive components means you will generate, whether you like it or not, 1/F noise or flicker noise. And this is a baseband spectrum, occurs very close to DC, and comes out in frequency as a function of the device technology, the biasing circuitry. Everything you do to that amplifier will affect the amplitude and the bandwidth of that flicker noise. Now, at many circuits, we have predominantly two different categories of amplifier. We have bipolar and FET-based. Our bipolars are realized with HBTs, and the FET-based are realized with PAMPs. If you take basically apples to apples, roughly the same size HBT, same size PAMP, the HBT will have better additive phase noise than a PAMP. You can pretty much guarantee that. When you start looking at the individual devices themselves, the larger periphery, the largest area in either one, with the lowest amount of current, will produce the least flicker noise. You take a small device, small periphery, small gate length, small base width, put a lot of current through it, you'll have a higher flicker noise component. So it's very important that you understand that. And with regard to the PAMPs, pretty much in general, a 0.5 micron will perform better than a 0.25, will perform better than a 0.1, etc. So keep that in mind. Now, if we take this spectrum and now measure it on a phase noise analyzer, what we're showing here is the power spectral density of the random phase. We don't measure that with our analyzer. We measure the additive phase noise, which is L. But you can see here, when you express this as dB, specifically dBc per hertz, then the power spectral density is related to the phase noise simply by a factor of 3 dB. And you can see what happens here. You have this flicker noise, this 1/F noise. It's called 1/F for a reason, because it rolls off at 10 dB per decade. And it's just going to continue down. The B-1 is going to be where that sits. Where does that intersect, say, the 1 hertz axis? Where is it? Well, it's a function of, is it a PAMP? Is it an HBT? Do I have active bias circuitry? Do I have passive bias circuitry? All the things you put into that amplifier are going to affect the magnitude of where this crosses, but the slope is always going to be the same. All right. So what happens now? Well, it's going to intersect what? Eventually what? It's going to hit that white noise floor, right? And this is a little counterintuitive at first, but you can see the power spectral density of the white noise, the B0, is proportional to the noise figure, as one would expect. And it's shown here as being proportional to 1 over the input power. So as you raise the input power, the white noise goes down. Not really. Don't forget, this is a dBc measurement. So assume you have noise power, it doesn't change. As you increase your signal power, right, your signal noise ratio is going to improve. So that's what's being illustrated here, that as you increase the signal power, the signal noise ratio improves, assuming, big assumption at some point, that the noise power is not changing. Because once the noise power starts to increase, then your signal noise ratio may actually stop increasing, and as we'll see, it might actually invert. So two kind of common or logical things to ask is, well, how low is low and how high is high? What does that mean? Well, we'll go into that. And something that we'll find useful just in general, and this is a little bit non-intuitive. One would not expect this just on face value. But when you're, for example, looking for a mimic amplifier, a lot of times the manufacturer won't give you a lot of information as to what's inside. Maybe if it's a bare die, you can get a blurred image of, oh, I kind of see, it's a Cascade. It's got 3 common source stages in Cascade. Maybe it's got feedback, maybe it doesn't. Maybe it's reactively matched. Oh, I see this one's got line couplers. It's a balanced amplifier. So you can get some indication by looking at the bare die. But look what happens. In the Cascade, the white noise power basically follows Fritz's formula. Okay? Mostly set by the first stage. If these are identical here, then you get some contribution from the second, whatnot. But you can see it's fairly constant and set by the first stage. But look at the 1/F noise. It goes up by 3 dB times log base 2 of M, where M is the number of stages. That's not intuitive. So you cascade amplifiers, you're degrading your 1/F noise, whether you realize it or not. You put amplifiers in parallel, noise figures are roughly the same. Assume we have Lang, lossless Langs, this is a lossless analysis. But the noise figure is the noise figure. But look what happens to the 1/F noise. It improves by 3 dB times log base 2 of M. So when you're doing a system design, you can take advantage of this fact. And as we'll see, designing the system such that each amplifier is inputting and outputting a specific amount of power becomes very challenging to avoid certain nonlinear regions. So this will come in handy a bit later on. So let's go back and say, all right, let's take some measurements of those 2 states, the low power and high power. What's low power? Well, in this case, we have an LVA 273 PN+, which is an HBT distributed amplifier working to 27 gigahertz, very, very broadband. And we're measuring it at different frequencies at a fixed input power of -7. So what do we notice here? Ignore this. We'll get into this later. But what do we see out here? And this brings up 2 interesting points. I get a call, measure the additive phase noise. I'm lazy that day, I'm gonna measure it at -7. The customer doesn't say, oh, I want the additive phase noise measured at a specific power. All right, so we ended up, wouldn't do this really, but we ended up measuring at -7. I get -162 at 10K. Now I'm gonna tell the customer I have an HBT distributed amplifier that achieves -162 dBc per hertz at 10K, then I'm gonna buy it. And I'm gonna look pretty stupid. So the input power is very important because what this is meant to show is actually the noise figure of the amplifier. If you're not familiar with this equation, you can determine the noise figure of the amplifier in the presence of a signal by measuring the additive phase noise in the white noise region. Very important. We're going to use that equation repeatedly throughout this webinar. Now, if you look at this, you see 2 gigahertz. It goes down, 6 goes up a little bit to 7. What's that? You're telling me the noise figure is worse at 2 gigahertz than 6? That doesn't sound right. No, it's a distributed amplifier. This extremely accurately predicts the noise figure performance of that amplifier as measured with a noise diode. So very useful. We're going to take advantage of this later, especially when this PN starts to get high. All right, so that's low power. What about high power? How high can we go? Well, first, we got to understand what our test set does. Because ultimately, the high power is going to give me the best signal-to-noise ratio. We need to understand what are our test set limits. Well, this kind of tells you. Now, we said we're going to come back to this. See, it's here, independent of the device. There's no device here. This is just the test set through path. So you see a lot of strange things here that we'll go into. Some of this we can mitigate using that technique I mentioned earlier where you adjust the source power down, 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 and you might notice that some of this peaking will be reduced. You go, okay, you know what? I'm not going to run it at +13, I'll run it at +10 because I eliminate this, it looks a little bit nicer. All right, so that's something we know how to address. This is really a pretty strong function for this analyzer of phase length. The longer that path is from input to output, you tend to get this climbing of the additive phase noise above 100 kilohertz or so. You can see it's not the DUT, it's in the test set, so maybe you need to explain that to the customer or your boss. It's not my amplifier, it's the test set. And then you see some kind of strange things in the middle here. And what's going on? You got this deep valley here, is that real? This one has a hump that comes up. These don't look too bad. So what's all that? Well, it could be something called cross-spectral collapse. And this next slide, you can see the reference here, gives you 3 examples of some of the shapes one might expect if you're being influenced by cross-spectral collapse. We won't get into it, but if you have like power supply noise or AM noise or different types of processes that are correlated and uncorrelated, you can get these funny shapes. You don't need to explain it too well, just know that it could happen. It could happen, and when you're looking at the response, you gotta kind of say, do I think my device is really 193 at 10K? I don't think so. So you'll know when it's a true measurement and when it's not. And you change the setup a little bit, change the frequency a megahertz or so, change the power a little bit from the analyzer. Maybe it goes away, maybe it doesn't. Add some filtering on the DC. Try something, and if it changes much, it's probably one of the 2 phenomena, excess phase length or possibly this cross-spectral collapse. So now let's again go back and look at how high can we go. So again, here's our favorite LVA 273 again. And we're showing the effect of increasing the input power. See here, we go to this bottom we're calling the optimum, and this is 4 dB less. And as we increase the power, just like the graph said, the white noise power looks like it's improving. It's really the signal noise ratio. Very interesting, I don't know that I mentioned this, but look at the 1/F. It doesn't really change as a function of power. It doesn't really change as much as a function of power or carrier frequency. Again, it's an up conversion process. That process doesn't care where the frequency is to a large extent, and it doesn't care what the power level is to a large extent. So this kind of indicates you have a good measurement. It's increasing with input power. The 1/F region is not changing. That's a good measurement. It's inconsistent with the small signal theory. Well, now let's go the other way. Now let's look at how high can I go again, but I'm going to change parts here. And I want to reiterate, this effect is not unique to this part. Every amplifier will experience this type of behavior. This just happens to illustrate the behavior at a power level that we can produce with our test set. So if you look what's happening here, this is the optimum noise power. And then as you increase in 1 dB steps above that, look what happens. You're killing the 1/F and the white noise. You're degrading it significantly. Whoa, what's that all about? That wasn't any of those charts we just showed. So this is a nonlinear effect, nonlinear distortion, really present in all amplifiers. We just happen to be noticing it here. And let's look at the next chart and you'll see this presented slightly differently. So here we have additive phase noise at a 10 kilohertz and 1 megahertz offset for both parts as a function of input power. And you can see for the LVA at 2 gigahertz, keep going, I'm happy, right? You keep increasing power, both flicker and white noise just keep improving. At plus 11, this part is over 8 dB compressed. So you can see good performance really has nothing to do, in this case, with the compression point. Here I'm saturated. This is not even compressed yet. Yet I'm seeing this inversion of the phase noise in both the flicker and the white noise regions. Interesting. So what's that all about? Well, remember I said earlier, as your signal power comes up, your signal to noise is improving until it's not. What happens if the noise power is a function of the signal power. So as you increase the signal, the noise starts to come up with it. At some point, if the noise power is increasing faster than the signal power, you'll get this inversion. So this indicates the point where you're degrading the noise figure faster than you're increasing the input power. And that's what creates this inversion or this inflection point. And again, has nothing to do with this part. It's just that it happens to occur at a power level that we can input from our test set. You see at 2 gigahertz, we can't get there yet. But as you see on the next slide, we believe that this inversion that you're seeing is a function of the AM to PM distortion of that amplifier. And there are some papers that I'll reference later that also describe this phenomenon. So what we have to do here is we use our P&A to measure the AM to PM of each amplifier. And you can see here's P out versus P in, here's gain versus P in, here's phase versus P in. And AM to PM is described both ways. We like to look at it as the derivative or the slope of this curve over 1 dB step in power. When you do that, you get AM to PM in degree per dB, and it has this characteristic shape. And the P&A will give you this directly. You can either get this yourself by performing the differentiation in Excel, or you can get this directly from the P&A. But look at the difference in these two curves at 2 gigahertz. All right, barely reaches 0.7 of a degree per dB. That improves. Where this guy is, he's up at a little over 5 degrees per dB. Very different AM to PM performance. Where did that inflection point start to occur? Well, somewhere around here, maybe 2, 3, right in this region. You know, we start to see that inflection point occur. So if we look, we're about here. So you can see we're not even 1 dB compressed, but we have significant AM to PM distortion. And that AM to PM distortion is causing the effective noise figure of the amplifier to increase faster than the signal power. So that's the whole reason for that inflection point, where if you look at the LVA at 2 gigahertz, it has almost no effect because it's so low. Now, if we do this across different carrier frequencies, we see something very interesting. So that, again, this is the LVA 273. And we're measuring this from 2 to 8 gigahertz. So you're like, oh boy, that's not good, right? So that means that if I had measured this at, say, 6 gigahertz, I would have seen the same thing. I would have seen a minimum and an inversion. I just can't get enough power at 6 gigahertz. We happen to do it here with GVA, happen to show this effect at a low power level. But what does this tell you? It says that if I operate in this region, I'm not going to get the additive phase noise that I think I am, because I'm in a region of very strong AM to PM distortion. And that is going to cause the noise figure, the nonlinear noise figure, to increase faster than my input power, and I'm going to degrade my additive phase noise. So either you have two choices, kind of operate down here or operate up here. And that's really the system designer's responsibility. Can I operate at 8 dB compression? I don't know, you gotta tell me. Can I operate over here and only get, that much output power? If I put in 0, I get plus 15, is that enough? If I put in minus 3 and I get, I get plus 12 dBm out, is that enough? I don't know, it's up to you. If I operate here, is 6, 7 dB of gain, of compressed gain, enough? Well, I don't know, maybe I gotta start cascading amplifiers now to get this. We gotta start cascading amplifiers. We know what happens when we cascade amplifiers now. All right, so it becomes very interesting to try and get a good system design where you're not degrading your additive phase noise, and you're trying to select where I operate and get a cascade of amplifiers to drive each other without just adding more additive phase noise. So this is an interesting chart because now it shows the 10 kilohertz and the 1 kilohertz additive phase noise. We're back on the LVA again as a function of input power. And I want you to think about that AM to PM curve we just saw. So look what happens. As you increase your signal power level, everything improves, as it should. as it should. We're in small signal now. Notice that the 2 gigahertz is higher than everything else. Well, we expect that, right? We know the noise figure is 2-3 dB higher at 2 gigahertz than some of these other frequencies. All right, so we got that. Then you can see it kind of comes again, it plateaus a little bit, and then it starts to improve again. But look at the other frequencies. That's why I said you're going to see this with any amplifier. The GVA just happened to demonstrate it at a convenient power level. But look at this, it comes down, you get this region where it's kind of minimized, and then what happens? It starts to degrade again. So here's that inversion in the additive phase noise that we alluded to earlier. And you can see it gets really bad when you go from maybe 5 and above, 5 dBm and above. And if you go back, well, look where all these peaks are. Okay, they're in that region. So this is a great thing to measure. If you haven't done it, measure this on your, when you're measuring P1 dB and IP3, throw AM to PM in there. It's not that difficult. The PNAs do it very easily, but it's great to understand what these curves look like, because if you're operating at a fixed frequency at 2 gigahertz, 3 gigahertz, not gonna bother me. If you're sweeping from 2 to 8, I've got a problem here. I can't operate at, for example, +6. My system analysis says I only need to hit this amplifier with +6. I can't do that now if you're really worried about additive phase noise. So this is now that large signal region where we said we were going to go into. And you can see it's really a very strong function of AM to PM distortion, which you really should characterize as part of the amplifier. You've heard me mention this noise figure formula again. We're going to use it again here because this is very interesting. I love this curve. It shows for the LVA, you start out at small signal. Okay, each of these points represents the small signal noise figure. You just run a line up from there at 1 dB per dB. All right, 1 dB, 1 dB, 1 dB, 1 dB. And you compare the slopes of these lines compared to the 1 dB to 1 dB. So you can see here for the GVA, it's very good. The noise figure really does not change much over input power. In this region, it starts to equal, and then look, it takes off here. So this tells me the noise is increasing faster than the signal. Another indication that's where that inversion is going to occur. You look at the LVA, it never really gets there except maybe this last little segment where it starts to equal the 1 dB per dB. So with that, I left you a bunch of references. I think we've answered, hopefully, what is additive phase noise, how we measure it, at least at many circuits, and how to specify it. There was a few examples where just asking for additive phase noise is really not sufficient. You have to understand it's the relationship between input power, additive phase noise, and carrier frequency in the large signal region. And all of a sudden, AM to PM distortion should enter into your conversation because it could significantly affect how that amplifier performs over a wide dynamic range. So thank you very much for your attention. I hope you learned something. Thank you.